thank you, John, for the introduction, Martin, and John also for the invitation to present here. It also feels like going a little bit full circle because John didn't mention it, but when I was doing my PhD work, I was kind of a PhD orphan, and people of the department adopted me and actually it kind of invited me to spend time in the department to do some of my PhD work. So I'm always forever grateful for that. I've seen lots of seminars with everybody here. I've gone to had a few visits at Rogue Brewery after the seminar, and I wish that I could do it this time round, but maybe hopefully once travel opens up we can do it in the future. So yeah, I'm also really excited about giving this presentation because the second half of it is actually a lot of stuff that I've actually never presented before. And so I'm really grateful to have the opportunity to actually share these new results. And I hope that people don't mind being a test case as I start to develop effective ways to kind of deliver this material. And for this presentation, we are going to look at the fun and kind of interesting ways that magma, volatiles, and climate are going to interact with continental rifts as they evolve and develop. So to do this, we are going to look at the East African rift system. And before I begin, I just want to point out that a lot of the data, a lot of the ideas that you're going to see here, I can't attribute it all to myself, right? A lot of friends, collaborators, and scientists have provided ideas that are presented in this talk, as well as, of course, all of the generous funding sources from both governmental and industry sponsors. So for this talk, we're going to look at the evolution of continental rifts. And I like to just kind of get the thought process going by throwing out just a couple of really broad and fundamental questions that relate to studies on continental rifting. How is continental breakup initiated? By that, I mean, what sort of processes are at play that help to break apart really thick and strong continental lithosphere to initiate the continental breakup and even the continental drift process? And also, how do continental rifts develop? How do they start and then evolve through time to the ocean spreading centers that we see today on our ocean floor? And so for your reference, I've just thrown up a couple of examples of active continental rifts that we see in the world today. We have the Baikal Rift in Russia, the Taupo volcanic zone in Aotearoa, New Zealand, which is an example of a rifted continental arc. We also have the Rio Grande Rift in North America, and then we have the focus of today's presentation, the East African Rift. So the East African Rift forms the southern arm of a triple junction. It's between the Red Sea and Gulf of Aden rifts. And this the East African Rift is classically divided into these eastern and western branches, where the eastern branch is thought to be the type example of magma-assisted rifting, and the western branch is thought to be comparatively magma poor. So these differences in the role of magmatism and rifting are emphasized on this figure that we can see on the left here, which shows us the distribution of rift volcanism in eastern parts of Africa. And what we see is that we have significantly more volcanism in the eastern branch compared to the west, and hence magma is more involved in the rifting process in the east. Then we have this figure on the right here, which shows us a seismic tomography model below the eastern part of the African continent. It's down to about 1,200 kilometers depth. This is from Malibo and Naiblade. And what you can see are these red zones in here, which represent anomalously low S-wave velocities at depth. These low velocities could be attributed to sort of elevated temperatures, which then can induce greater melting. So based on all these observations, we can assert that we probably have higher magma input in the eastern branch, right, and less in the west. So things kicked off in East Africa about 30 million years ago with the eruption of the Ethiopian traps flood lavas. Rifting then initiated at about 20 to 35 million years ago in some discrete regions. And since that time, the rift has gradually propagated southward, as is illustrated by the ages of some of the earliest rifted lavas in sectors of the eastern branch. Now, these ages show us that as we go south, the rift is going to get younger and younger. And this younging of the rift is really fortuitous because it's going to provide us with snapshots of rift basins at different stages of their evolutionary process. So we can look at how the architecture of a rift is going to evolve through time in the eastern branch. So this idea was first explored by Hayward and Ebinger, who looked at rift architecture in Ethiopian sectors of the rift. What they saw was, as they went from south to north or from younger to older, that strain was first focused on faults on the rift borders, and then through time, this fault strain migrated into the rift center, and rifting became progressively more and more magmatic. So based on that study, as well as many others since, we now have a simplified conceptual model for how rift basins evolve in the eastern branch of the East African rift. So from about 0 to 5 million years, strain is focused on the rift borders, on what we call border faults. Then from about 0 to 5 million years, it migrates into the center of the rift, into what we call intra-rift faults. Between about 10 and 20 million years, rifting becomes progressively more and more magma involved. We start to develop what are called magmatic segments, which are thought to be nascent spreading ridges. Then after about 20 million years or so, seafloor spreading fully kicks in, and we're now accreting new oceanic crust and lithosphere. And this presentation will in part be exploring and testing this exact model of rift evolution. So in particular, we're going to focus on how fault system development is impacted by magma, volatiles, and climate. And we're going to do this in 3 parts. In the first part, we'll look at early stage fault development and how it is impacted by the release of magmatic volatiles and associated fluid weakening. In the second part, we're going to look at fault development during the establishment of magmatic segments. So we're going to look at how magmatism can focus fault strain. And then we'll finish by exploring how fault system behavior can be impacted by climate. Okay, so that brings us to part 1. We will look at how magmatic volatiles interact with fault systems during the earliest stages of continental rifting. And this is based on this paper here in Geosphere, as well as some other accompanying works. Okay, just quick refresher of that conceptual model I just showed you, right? At the earliest stages of rifting, strain is focused in these conceptual models on the rift borders, then it migrates into the rift center, into inter-rift faults, and then magmatism becomes more and more involved in rifting as we evolve to a spreading ridge. So for this part, we're going to focus specifically on this transition here, the transition from border faulting to intra-rift faulting during early stage fault, rift development. We're going to ask 2 main questions. When does the transition occur? And is this transition linked with the release of magmatic volatiles? So these magmatic volatiles are ultimately going to be mantle volatiles. And so it's nice to just start with a simple conceptual picture of how mantle volatiles can be mobilized during continental rifting. So in this example, we have the melting of a sinosphere and incorporation of mantle volatiles into magmas. They rise through the lithosphere intrude into the lower crust, where they're going to cool and crystallize and release these mantle volatiles through fault infraction networks that are going to be forming in our extending continental crust. So if mantle volatiles are actually going to be driving strain localization, we would need to see evidence for the following in an active continental rift. We would need to see evidence that magma is entering the crust. We'd also need to see evidence that we're getting release of mantle volatiles along fault systems. Then lastly, we would want to see evidence for these mantle volatiles focusing fault-related strain. And we will address these questions here, right, in this first part. And I'll do this by providing a mix of geophysical, geochemical, and structural geological observations that are going to support these three key ideas. To do this, I'm going to look at the Magadi and Natron basins at the Kenya-Tanzania border. These basins are 3 and 7 million years old. So we're going to be looking at relatively early stage continental rift development. And then to give you an idea of the crustal structure of these early stage rifts, I'm going to show you some seismicity and geophysical data. So in 2013 and 2014, Cindy Ebinger and others, they set up the 32 station CRAFTI seismic array. You can see the seismic stations right here as these purple triangles. During this time period, more than 3,000 earthquakes were detected on the array. And then based on these data, Steve Roca put together a crustal tomography model for the regional velocity model for the region. Here we have a cross section through his velocity model, right, from west to east, down to 40 kilometers depth, right? These red zones show us anomalously slow S-wave velocities. And in general, we can see we get low S-wave speeds below our rift system. So these shallow low velocities here probably represent basin fill sediments and volcanics. But perhaps more interesting is this low S-wave velocity zone here, which perhaps could signify the presence of lower crustal magmas. And then even more interesting, at least I think, surrounding this low velocity zone in the lower crust, we've got swarms of mid to lower crustal seismicity. These could represent potentially ongoing magma intrusion, or even potentially the release of magmatic volatiles along fault infraction networks. So to test whether volatiles are actually ascending along our fault network, we adopted the CO2 accumulation chamber method shown here. So with this device, we can measure CO2 coming up diffusely from below in the ground. We can trap it in our chamber, right? We have a gas analyzer with an infrared sensor that can look at CO2 concentration in our chamber here. And then by looking at changes in concentration through time, we can get a flux of CO2 coming up from below in the ground. So we used these chambers and we measured CO2 flux in and around fault structures all over both the Natron and the Magadi basins. I'm not going to show you all the data. We collected about 700 measurements, at least for this study, and more since. And then we also collected gas samples for isotope analyses, and we use these isotopes to understand the source of the CO2. So just in the interest of time, one quick example of our CO2 flux data. This is a transect across a faulted graben in the Magadi Basin. These red points here are showing us our CO2 flux values, right there in grams per square meter per day. We can see that on the y-axis. And to quickly summarize it, we see high CO2 flux in the vicinity of fault zones along transects like this. This suggests that our faults are acting as permeable pathways for the ascent of CO2. Like I mentioned, we can also sample these gases and analyze their isotopes to examine the volatile source. So this is our carbon isotope data for these two regions. We have the concentration of CO2 on the x-axis, high values are to the left here. We have delta 13 carbon on the y-axis. High amounts of carbon 13 would sit up high here. We also have the values we would expect for different sources of carbon, including the air, the mantle, and biogenic CO2. And when we interpret these plots, what we need to remember is that our samples are going to capture both air and also carbon from our various sources. And our data here fit really nice on a mixing line between what we'd expect for air and mantle carbon. So this suggests that we have a mantle carbon signature, likely because the CO2 is being released from deep magma bodies. Right, so in all, our first conclusion would be that we're getting magmatic CO2 degassing, probably from lower crustal magma bodies along rift-wide fault systems. So this then will bring us to our final question. Are mantle volatiles focusing fault-related strain? So we're going to be looking at where fault strain is located in the Magadi and Natron basins, and we're going to estimate this in the following way. First thing we're going to do is we're going to calculate the total extension in our intra-rift faults only. We will then look at the age of these faults to get a time-averaged extension rate. We will compare the extension rate for these faults to the extension rate for the entire basin based on GPS modeling from Sarrier et al. 2014. And then by comparing these two values, we'll come up with an estimate for the extension rate on our border fault. We will then look at where the highest amount of strain is located within the basin and then compare it to regions of magmatic volatile release to see if there's an association between high strain and the release of magma volatiles. So for the study, we're still focusing on the Natron and Magadi basins. As a reminder, the Natron Basin is 3 million years old. The Magadi Basin is 7 million years old. So if we compare where fault strain is located within these basins of different ages, we can think about how it may evolve through time, how fault systems evolve through time. So I mapped out all the faults in the area using aerial photography. You can see this map here on the right. We have the intra-rift faults in red. We have the border faults that bound the western side of the basins in black. So these fault maps were ground truthed during 3 different field investigations between 2012 and 2014. And then I measured fault throws using the 30-meter SRTM digital elevation model. In order to estimate the total strain accrued on the intra-rift faults only, we use the method of Schultz and Cowie 1990. So essentially what we do with this method is we sum the amount of total extensional strain represented by every fault in our fault population based on the fault's displacement, length, and depth extent. We multiply this by the inverse of the faulted volume. This gives us a horizontal extensional strain in our intra-rift faults. To convert the values to extension values to time averaged extension rates, we sampled lavas dissected by the faults and then dated these using argon-argon dating to get time averaged extension. So here we have our results from our extension calculations, again for the intra-rift faults only. So I'm showing 2 strain transects, one through the Magadi Basin at the top here, and another strain transect from Y to Y here through the Natron Rift. So again, we have distance on the x-axis, right, from west to east. Then we have percent extension on the y-axis. And these gray points that you see on this plot represent the percent extension on each of these corresponding red boxes here. So what you can probably see immediately from looking at these plots, right? The main thing is that we get way higher extension accommodated in intra-rift faults in Magadi, right, compared to Natron, more in Magadi. Lastly, we dated the lavas that these faults dissect to calculate our time average extension rates. And these are the results that we got. So in the Magadi Basin, the intra-rift faults are accommodating way more strain at 1.6 millimeters per year of horizontal extension compared to Natron at 0.5. Like I mentioned earlier, we then compared these values for these faults to the extension rate for the entire basin based on GPS modeling. And by subtracting these two values, we can get estimates on our border faults, 0.4 millimeters for Magadi per year, and then 1.3 millimeters per year for the Natron Basin. So I kind of powered through that. And if anything was hard to follow, all you need to know from this exercise is that in the Magadi Basin, the highest fault strain is focused in the rift center in our inter-rift fault population. And in the Natron Basin, the highest strain is focused along the border, along our border faults. We know the ages of these basins. Natron is 3 million years, Magadi is 7 million years. So based on these observations, we're suggesting that we get a transition from border fault dominated strain to inter-rift faulting somewhere between about 3 to 7 million years after rift initiation. And this brings us to our final question in our journey here, right? Is there a relationship with strain and fluid flow? So keep the locations of high strain in mind on this image on the right here in red, because on the next slide, I'm going to pop up the position of hydrothermal springs that are coming up through the rift. So these yellow stars here show us the locations of spring systems in the region. We can see that in the Magadi Basin, fluids are rising up through the rift center, also where we're getting the highest amount of faulting. And then in the Natron Basin, they're rising up along the rift borders, again, where we have the highest extensional strain. This image on the left shows us a picture of the springs, right? They're fault parallel. They manifest at the base of fault scarps. So there does appear to be a structural control on fluid flow here. And then finally, we also sampled these springs to look at helium isotopes. We found that we have high values of helium-3. So a lot of sort of primordial helium values, which suggests that we have magmatic or mantle contributions to these fluids. So in all, we see a relationship between strain localization and the flow of magmatic fluids through our rift system. So we can summarize the first part of this presentation on this box diagram here. All right, we see low S-wave velocities in the lower crust, which likely indicates the presence of magma. These possible magmas are surrounded by swarms of mid to lower crustal seismicity, which could potentially support magmatic volatile release from those lower crustal magmas along fault infraction networks. Although we can't make that assertion based purely on the geophysics, we can make this assertion based on our CO2 degassing studies, which support the transport of magmatic CO2 along rift-wide fault systems. These faults exhibit fault parallel springs, right, with magmatic fluid contributions. These magmatic fluids rise through the rift in regions of high fault strain. And then lastly, as our rifts evolve and the location of highest strain migrates from the rift border to the rift center, so too does the location of magmatic volatile release, suggesting strong links between strain focusing and magmatic fluid flow during rift evolution. Okay, so I hope I've convinced you somewhat of a correlation between magmatic volatile release and strain localization during early stage rifting. However, by necessity, as you've probably noticed, these volatile transport processes are also linked with magmatic processes. And we're going to explore magmatism a bit more now in part 2 of this presentation. So in particular, we're going to look at the nature and distribution of faulting during the establishment of shallow to mid-crustal axial magmatism, during the establishment of what we call magmatic segments in this evolutionary model that we see here. For this, we have a new focus site in the eastern branch. It's called the Turkana Depression. So for your reference, before we were sitting here in the Natron and Magadi basins, so we've moved about 400 to 500 kilometers north along the eastern branch of the rift. As we head north, we expect to see more evolved systems. And this is the case here for the Turkana Depression. However, Turkana is actually somewhat unusual and anomalous in the eastern branch. Firstly, the Turkana Depression has localized right within a Cretaceous Paleogene rift system that immediately predated the East African rift. And consequently, the Turkana Depression, which we will look at, initiated in pre-thinned lithosphere. And another thing is that the Turkana Depression actually initiated early in this pre-thin lithosphere. So the syn rift stratigraphy here support rift initiation in about 25 to 30 million years in Turkana. It suggests that it's one of the oldest zones of rifting in the East African rift. And thermochronological results support a phase of exhumation even as early as 45 million years, although we don't really know how much extension occurred there. So what is my point? The Turkana Depression is an oddball for the East African rift, and it's hard to fit this into some of those evolutionary models that I showed you earlier. However, there is still a lot that we can learn about how magmatism and climate interact with rift systems when we look at Turkana. So the Turkana Depression is unlike many rift systems in East Africa in that it is a broadly rifted zone. And I'm going to call this zone, this broadly rifted zone from now on, the Turkana Rift. So here we have an annotated DEM of the Turkana Rift. Right here, we can see a series of basins. They are segmented from both west to east and also from south to north. These black lines here show us the positions of border faults that bound our different rift basin segments. We have all these different basin segments here: South Lokichar, North Lokichar basins, Turkana, Kerio, and South Turkana basins. And lastly, you might have noticed in blue here, right, we have this lake. So Plio-Pleistocene tectonic subsidence has allowed for the establishment of this rift lake here called Lake Turkana. It's a closed basin lake. It's about 50 to about 100 meters deep. The Turkana Rift also has an evolutionary history very different to other systems in the East African Rift. We can illustrate this by looking at both the general structure of the basins and their timing of formation. So right here we have a couple of cross sections, right, through southern regions. These are based on reflection seismic studies and exploration drill wells from the 1980s and 1990s. So in each of these cross sections, we can see that we've got these three basins segmented across strike, right, from Y to Y, here to here, X to X. We have the South Lokichar, the Kerio Basin, the South Turkana, and then north of that, the North Lokichar, Turkana, and Kerio basins. These gray regions here represent the pre-rift basement, and these white regions are showing us the syn-rift sedimentary fill. And in places it reaches up to about 7 kilometers in thickness. Hopefully you can also see that our basin fill thickens in many cases towards our border faults. And this suggests that the border faults provide the dominant control on tectonic subsidence in these basins throughout their history, at least. And finally, by understanding the ages of the different sediments that sit inside these basins, we can look at the broad timing of rifting in each of our basins also. So I've provided just one example to illustrate this to everybody. So this is horizon O. It's a high amplitude seismic reflector, right, that corresponds to the top of a lava sequence that's 4 million years old. The presence of this horizon is going to give us an indication of when our basins were rifting. So we don't see horizon O in South Lokichar. This suggests that South Lokichar began to rift before 4 million years and also ceased rifting before 4 million years. We see horizon O here in the Kirio Basin. We have sediments below it as well as sediments above it. This suggests that rifting initiated before 4 million years, but then also continued for some time after 4 million years to deposit these layers. Then lastly, in the South Turkana Basin, all the synrift stratigraphy is above horizon O. So this suggests that rifting began in the South Turkana Basin after 4 million years. So based on these kinds of relationships, this is the history of rifting in the Turkana Depression. And this is based on an interpretation from Morley, 1999. So firstly, in the late Oligocene, early Miocene, the locus of rifting was focused in South Lokichar, right here. And then what we see through time is that actually rifting is going to migrate both eastward and also northward. So skipping ahead quite far, we can go to the middle Miocene. We can see the locus of rifting was encompassing all of these basins shown here. Again, we're seeing an eastward and northward migration. Then by the early Pliocene, the westernmost basins shut down, right? Again, an eastward transition. And then as we head to the late Pliocene to present, we have a further eastward shift with the activation of the South Turkana Basin beginning about 4 million years ago. So hopefully from looking at these cross sections here and my spiel about the timing of evolution of the system, you should be able to see that the Lake Turkana, so the Turkana Rift system is different to your standard East African rift basins I showed you before. In particular, we have this wide zone of rifting, and strain is not focusing, at least through its history, its early history, into these intra-rift faults for at least 20 million years. Instead, we have rift basins migrating laterally, having lateral shifts in their positions and continued border faulting in most of these. Perhaps the key reason for this difference, and I'm speculating a bit here, is that for at least 20 million years, we don't get a significant amount of volcanism and magmatism in Turkana. So there are pulses of flood lava eruptions in the Lake Turkana Rift, but we have long hiatuses on the order of millions to tens of millions of years. So perhaps this pattern of rifting, which is different in Turkana, is more to do with a lack of magmatism. So with these points in mind, this brings us to an overarching question. Where is the modern locus of rifting today in the Turkana Rift? And does magmatism play a critical role in driving modern rifting? To address this, we're going to focus on the South Turkana Basin. Everything I show you from now on is going to be down here in this younger basin segment, the South Turkana Basin. And the South Turkana Basin is actually a great test case for thinking about magmatism because it is different to the basin systems to the west. Specifically, it has a large quaternary aged axial volcano, which is called South Island Volcano. So looking at fault patterns here, we might actually be able to see how magmatism could impact rifting in the Turkana Rift. And we're going to look at the South Turkana Basin through the lens of high resolution, single channel seismic reflection data. Right, these seismic data were collected in 2009 to 2011 by my postdoc advisor, Chris Scholes from Syracuse University. These black lines you see on this map here in the South Basin show us the position of all the different seismic profiles that they collected, and I'm going to show you a couple of these coming up. So here's one of these examples of these seismic data. You can see the position of the profile here as this yellow line from X to X. Please note that the depth is in milliseconds two-way travel time from the top of the lake. Basically, a value of 100 on this represents about 75 meters from the top of Lake Turkana. This package right here would be about 35 meters thick. So hopefully you can see from this profile that we have really high resolution data. It's high quality, and it gives us a high resolution picture of the shallow subsurface in this rift system. So here's an interpretation of this profile. Again, hopefully you can see that it's relatively easy to follow our different seismic horizons and also observe offsets in these horizons, which we can use to infer faults. And so this is a great data set for thinking about fault histories across the rift of the basin. An additional bonus is that a lot of cores have been taken from this basin, each about 5 to 10 meters long, 5 to 10 meters from the lake bottom. So this one here, this core here, 46P, is particularly useful because Morrissey and Scholes use this to build an age model to understand the ages of the different sediments you see in that seismic section. So I'm going to quickly show you how this age model was produced because it's important for some of the stuff I'm showing. So this is core 46P. It's in the basin. It's a few kilometers shown here, northeast of South Island volcano. This is where the core would sit in this seismic section right here. Here we have an age model for this core. It's built using the program Bacon. Bacon is made by Bloor and Kristen down there. And we have depth on the core on the x-axis, and then we have our age on the y-axis. Right, so what's this plot showing us? At different depths in this core, materials were extracted for radiocarbon dating at these different spots. These included ostracods, macrophytes, organic rich muds, and then these smaller blue shapes are showing us the position of the samples in the core and also their age with a degree of uncertainty, well, to 95% confidence. And so this Bacon model utilizes these dates at different depths in the core to build a probable age model for the different sediments. So this age model is the range of ages to 95% confidence are shown here in red. And then from here, we can take these ages and start to match it to the seismic data to get an idea of the ages of our seismic horizons. Right, so from this analysis, horizon 3 shown here is probably somewhere between about 9,000 and 10,000 years old. So in all, we have all the necessary ingredients that we need for a tectonic study here. We have our high resolution seismic data, which we can use to get fault displacements and look at the spatial distribution of extension. We have age constraints. From the age model, we would know that on this plot, horizon 2 is about 5.2 thousand years old, and horizon 3 is about 9.5 thousand years old. There are uncertainties for these. I'll show you those later. And because we have the age constraints, we can now get rates of extension in the basin by looking at the faults and knowing their ages. We can also, which I think is really interesting, and I'll show you at the end, we can think about temporal changes in fault behavior as well during different time periods. But firstly, we'll just have a quick look at the spatial distribution of extension and then rates of extension across our fault population. And I just had a lot of preamble, so I'm just going to remind the questions, like why we're doing it. We want to know where the modern locus of rifting is in the Turkana Rift, and we also want to understand whether magmatism plays a critical role in modern rifting. So how did we do this? Woo, firing ahead. So first, we map out that horizon 3 in every single one of our seismic sections. This is our 9,500 year old seismic horizon. The next thing we can do is identify rift normal faults based on how this horizon is displaced in our seismic sections, and we can do this across all of our seismic profiles. Next, we can measure throw on these faults, which we did by looking at the vertical separation of the footwall and hanging wall cutoffs along every single one of our faults. So based on this mapping, this is a structure contour map of horizon 3 across our basin. We have depth to horizon 3 in milliseconds two-way travel time. Essentially, regions in blue are regions of greater tectonic subsidence. Regions in yellow and red are regions of less subsidence. And these black lines, right, are our faults, which are primarily controlling the position of this horizon. So what does this show us? Straight away, we can see that we have focused fault subsidence along our rift axis. The subsidence aligns with South Island volcano. Right, and please note that a lot of these patterns that we're seeing are very different to western sides of the Turkana Rift that I showed you earlier, which are primarily border faults. Magmatism isn't involved much. We can also explore the distribution of tectonic strain further by looking at the along strike distribution of extension. Essentially, we can go from west to east along all our transects here. As we go from west to east, we can sum the amount of throw on all our faults. We can use these data to get an estimate for the total horizontal extension on our different transects. Then we can compare how extension values vary as we head from north to south. So here's our results showing how much extension is accommodated from a long strike away from South Island volcano here. Distance from South Island volcano on the x-axis, extension on the y-axis in meters. We have uncertainties based on the possible dips of our faults. What we see from these data is we're getting increasing extension towards South Island volcano. And we're interpreting this to suggest that we're getting that magmatism is focusing fault strain. So this suggests that magmatism in South Turkana plays a key role in driving our axial intra-rift faulting. Finally, we know the age of this horizon. It's about 9,500 years. And so we can get an estimate of the time averaged extension rates in the South Turkana Basin. And within about 10 kilometers of South Island volcano, we estimate extension rates ranging about 3 to 5.8 millimeters per year, just in this part of the basin. These extension rates are remarkably similar to the extension rates, the modern ones from GPS, across the entire Turkana Rift. And because they're so similar, we believe that Holocene extension in Turkana is primarily focused in the South Island Basin, the South Turkana Basin, at least in the Holocene. Furthermore, about 80% of the time average extension occurs along the rift axis right here, and it aligns with South Island volcano. And so rifting appears to be focused within a recently developing magmatic segment. And these kinds of patterns are really different to what we've seen in the past in the Turkana Depression. And it shows us how magmatism can act to localize fault strain. Okay, so that is how extension is spatially distributed in the South Turkana Basin. Finally, we can take advantage of our age constraints to examine possible temporal changes in faulting. And in particular, in this last part, we will examine how fault behavior within a rift can be impacted by changing climate on 1,000 to 10,000 year timescales. And we're going to stick with the Turkana Rift to do this and examine how climate-induced lake level change has impacted fault behavior and rift development. So in Lake Turkana, like many basins in the East African Rift, we have a fluctuating lake level, and it fluctuates based on regional climate in East Africa. Right, so depending on what the climate's like, whether it's wet or dry, Turkana goes from high stand phases where the lake is overflowing to low stand phases, where it's a closed basin lake. All of this is dictated by climate, and we can illustrate this on this plot here. So this is from Morrissey and Scholes. This is the lake level in Takana. We have the present day on the right, all the way back to about 800,000 years ago. Lake level on the y-axis, right? What we see is that between about 5,000 and 8,000 years ago, Lake Takana was at a high stand phase, sitting quite high during what is called the African humid period, a regional climate period across East Africa. Then about 5,000 years ago, we transition away from the humid period to a dry period, what I'm calling the post-humid period. The lake drops in response by about 100 to 150 meters. So what we're asking to study is, what were slip rates like on our faults during the African humid period when we had a high stand, and what were the fault slip rates like during the post-humid period where the lake level dropped? So we're asking, do we see a change in fault behavior resulting from this climate transition right here? So to show you how we examine secular changes in fault slip, I'm going to show this fault here as a possible example. At this exact location, I can measure the throw on a fault on an horizon, and I can also get its age and plot these on this diagram. So we know that horizon 2 is 5.2 thousand years old. So it sits somewhere on this plot at 5.2 thousand on our age. And if I come across a fault that displaces this horizon by 3.5 meters, I can plot this data point right here on our graph. Next, we know that horizon 3 is about 9,500 years old, sitting here at our age value. And if I go back to that exact same fault, and I see that we've got 4.6 meters of throw on that horizon, I can drop a point right here on this plot. So these are our 2 points here for our two different horizons, and they're super useful, right? Because these represent distance and time values. So therefore, the slopes of the lines related to distance and time are going to relate to rates, and in particular, they're going to relate to slip rates on these faults, as well as slip rates during specific periods of time. However, there's one more caveat to this kind of analysis. These actually aren't unique solutions, right? Because we do have uncertainty with our initial inputs. We have uncertainties related to the age model, right? And those are represented by this black line. We have uncertainties related to the fault slip. And that's related to how we convert seismic velocities to actual distances. So actually, the true value rests somewhere in these boxes here. And this means that there is a range of possible sort of throw or slip rates or time paths that we can go through with our analyses. So to account for the possible range of throw time paths, we ran a series of Monte Carlo simulations using these age and throw constraints for our different horizons. So here are 1,000 simulations from this fault. Note that the fault has more than one possible throw time path. And based on the slopes of these lines, there are a range of possible slip rates, but some slip rates are more probable than others. So what do we do with these data, right? We've got to remember that what we care about here is what are fault slip rates like before and after the African humid period, which is this time period roughly here on this plot. So the slope of this blue line here gives us the slip rate on the fault during the African humid period when lake level was high. The slope of this yellow line gives us the slip rate after the African humid period where the lake level dropped. And if we subtract these values off each other, we will get a change in slip rate, how the fault behavior changed in response to the climate, in response to the transition from the humid to post-humid period. So we did these kinds of analyses on like 27 of our faults, 27,000 simulations, 1,000 simulations for every fault. So I'm going to show an example of just one of these simulations. This is for fault 10. It's a frequency histogram of fault slip rates. We have slip rate on the x-axis, frequency on the y. Essentially, you can imagine these as probability density functions, showing us the probability of different time average slip rates during our different time periods, with the different time periods being these different colors. The orange here shows us the frequency distribution of fault slip rates during the African humid period. The blue data here shows us the frequency distribution of fault slip rates after the African humid period. And like I mentioned, if I subtract these values, I can get a change in slip rate as we transition out of this different climate phase. So this is shown here on the right here. We've got slip rate and frequency again. And just eyeballing this, we have an average change in fault slip on this fault of about 0.25 millimeters per year. And based on the distribution of the data, we're about 99% confident that we are seeing a increase in the rate of slip. We're very low on time, so I'm just going straight to sort of results. Please don't try to look at the data on this table, but which is showing us the mean change in throw rate and standard error for every fault that we analyzed. And to summarize, what we find from these analyses is that for every individual fault, on average, we get a mean change in throw rate or slip rate of 0.18 millimeters per year as we have a drop in lake level. Now, this may not seem like a really large value, right? But remember, it's the average change for every single one of our 27 faults. So if we think about all of these faults collectively, we're looking at an increase in the rate of extension within the basin of more than 1 millimeter per year, at least 20% faster for during the last 5,000 years, at the time when the lake level had dropped. So in all, we're seeing a correspondence between lake level fluctuations driven by climate and an increase in fault slip rates. And again, we don't have much time, so I'm not speculating on the potential causes for this, which will take us open. And instead, I'm just leaving this as an open question, which I'm happy to discuss about whether there is a causal effect here. And this is the next step in our work to really investigate this causal relationship with numerical modelers, investigating how lake loading, for instance, can impact both magmatic behavior and fault behavior in our rift systems. Instead of getting into that, I'm just finishing off by throwing out a few broad conclusions that summarize our work here. So what we see is we get significant volumes of deep CO2 that are being released along rift-wide fault systems in continental rifts in the East African rift system. We're seeing that the transport of magmatic fluids, including this deep CO2, may assist in rift basin evolution and the evolution of fault systems. We see that extension is also preferentially focused into developing shallow magmatic systems in East Africa. And finally, we're finding that climate change may have an influence on the rates of faulting and the behavior of our fault basins. And with that, I hope I'm on time. Yes, just got there. Thank you everybody for listening. Thank you again for the invitation. More than happy to chat about it.